All right, I wanted to make a quick little video walking through the applications of normal distribution. This is going to go quickly, so you can rewind these as much times as you would like. First example from class, example 2, the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. Now, I know that I don't like to teach with kind of models, step-by-step models, but in this case, I have developed one, and we're going to walk through those 5 steps here as I walk through this problem. The first step is going to be to sketch a normal curve. So I'm just going to come in here and I'm going to sketch my normal curve. I'll do that here. I know the normal curve is going to be a bell curve here. Step number 1 is complete. That's my first step. Just sketch the normal curve. Next step, add the given data. So I've got some given data here. So there's my next step. Next step, add the given data. I've got some data. I've been told that the mean is 268 and a standard deviation of 15 days. So let's go ahead and come in here and let's add that information to my bell curve. I know the mean is going to be, let's draw that a little better. The mean is going to be 268, and I know that my standard deviation is 15. I'm going to add that up here in the top. I kind of just like to add it up here above to make sure I know what I'm doing. Okay. Let's see. The next step there, I've got the example. So add the given data, check. So now let's look at my next step, and it's going to be shade the region discussed. Now to shade the region discussed, I've actually got to get into the example of the problem, or example 2A. I've done everything I can with example 2, so now I got to move on to the region that's discussing. One classic use of the normal distribution is inspired by a letter to Dear Abby in which a wife claimed to have given birth 308 days after a brief visit from her husband, who was serving the Navy. Given this information, find the probability of pregnancy lasting 308 days or longer. So, first thing I identify is I've got this 308, and I've got to figure out where I can place that 308 on my data curve. Well, I know that that's my, what I'm really measuring down here along the x-axis is it's not just 268, it's 268 days, because that's what we're measuring here, the number of days in a pregnancy. So if I'm looking for the data that I've been given, 308, it's going to be roughly over here. Now, I don't know exactly where it is, but I know it's going to be to the right somewhere. And if I'm looking for the probability of something 308 days or longer, so picking something 308 days or longer, I'm going to be looking for the area to the right of that blue line. Hopefully you've got that down. It's very important to identify which area or which region we're looking for. And what I'm looking for is the probability or the area of that region. That's what I'm trying to figure out. That's my unknown. Now, the good thing about what we've been studying is the area is the exact same idea as probability, because the area is directly correlated to the probability in these types of problems. So I can calculate that. The other thing that's really, really nice is we've got a calculator that will do a lot of the heavy lifting for us. So in the calculator, I'm going to write normal CDF, and it's going to ask for 4 numbers. The first number I'm going to add is going to be the value that I'm starting measuring the area from. In this case, I'm starting measuring from 308. Next number is going to be the number that I'm going to stop measuring area to. In this case, I'm just going to put 10,000. It doesn't matter exactly how many zeros I put in there as long as I'm well far out. I'm going to put 10,000. The third number is always going to be asking for the mean. In this case, it's going to be 268. I'm going to write down here vertically. Then the last number is going to be the standard deviation. In this case, it's going to be 15. Typing that into the calculator should give us a value of 0.0038. Now, you've got to interpret what that means. What this is saying is this is an area, right? What I've calculated here in green, this is an area. So I've got to think about what does that really tell me? Well, that's really telling me a probability, and what that's telling me is that I've got a 0.38% chance that if I picked a random person, their birthday would take, their pregnancy would last 308 days. That's 0.38%. That's a very low percentage. So what does that tell me about the situation? Well, it suggests that the conception of this birth was not at 308 days ago. It means something else was awry. I'll let you determine what that is. Moving on to the next problem, same situation. I've got a pregnancy that's normally distributed with a mean of 268 days and a standard deviation of 15 days. First step I'm going to do is I'm going to go ahead and draw that normal curve. So here's my normal curve. I've got a bell-shaped curve. Next step is going to be to add what I've been given. I've been given a mean of 268, and I'm going to write down my standard deviation of 15. So I've set up everything that I know in the situation. Now let's figure out what I'm trying to solve for. In this case, I'm trying to find the length of pregnancy in the lowest 4%. Well, 4%, hopefully you should be thinking to yourself, okay, 4%, that sounds like a percentage, and when I think of percentages, I think of probability. And in this case, when I'm talking about probability, I'm talking about area. So what this is really asking for is, where is that lowest 4% located at? And hopefully you're thinking, well, the lowest 4% is going to be over here to the left, and it's going to be this area right over here that's equal to 0.04. Notice that it was not equal to 0.4. That is not 4%. 4% is 0.04, and you've got to be very, very careful about that, okay? So this is the area that I'm looking for, that 0.04. And what I'm really asked for is, what is the number of days that defines that area? That's what I'm trying to figure out. Now, the good thing about this is we've got a calculator that'll do some of the heavy lifting for us, and we've got a function called inverse norm. And if we type in inverse norm, it's going to ask us for 3 numbers. The first number is the area to the left of the value. In this case, the area to the left we're looking at is 0.04. The next value it's asking for is the mean, and then it's asking for the standard deviation. When you type that into the calculator, you should get 241.74. Now, it's really important for you to be able to interpret these answers. In this case, 241.74, this is a data value. It's along this x-axis, and along this x-axis, I was measuring data. And it was 268 days earlier, and whatever the data is, that's what my answer is going to be. In this case, it's days, so I've got 241 days. So if I was to interpret this problem, the question was asking how many days old is a baby that is satisfied as premature. In this case, it's any baby that was 241 days or lower. And the reason it's lower is because what we're really looking at is this point and then everything to the left. Got a little bumpy there, but hopefully you followed along with that. All right. Example 3. In this case, engineers must collect the breadths of male heads while designing motorcycle helmets. And men have head breadths, let's just call it head size. They have head size that are normally distributed with a mean of 6 and a standard deviation of 1. So, same thing that I'm going to do always, I'm going to draw the normal curve. So here's my normal curve. It tells me that the data is normal, so I can just draw my normal curve. Bam, there's my normal curve. Let me see if I can move this curve down. Oh, no, I'm just going to stay right there. That's cool. So, next thing I'm going to do is I'm going to add the data that I know. I know that my mean of 6 and a standard deviation of 1. Mean of 6, standard deviation of 1, so I'm going to go ahead and add that to my normal curve. Mean's always going to be inside this very center of that normal curve, and then my standard deviation, I'm going to write that up here. If you wanted to add more like distance measurements on this normal curve, you could do it by using the rule of 68, 95, 99.7, but for the sake of these quick examples, you do not have to do that. I would recommend you drawing a picture like we've done. Next question, we've added all the information we can do. Now let's figure out what the question's asking for. What percentage, that should be telling you several things. Hopefully you're saying, okay, what percentage? That's going to be asking for a percent. And when I think of percents, I think of probability. And in these types of problems, when I talk about probability, I'm talking about area. So it's asking me for an area, or it's asking me for a probability. That's a good thing. Okay. What percentage of the adult male population has a head size that is too large for the small helmet, which measures a head size of 4.75 inches? Well, we've been given some more information here. It looks like we got 4.75 inches, so let's go ahead and add that to my graph. Identify that 475, then you got to figure out what that is. Well, if we come back to our graph, we can see that this 6 on the x-axis is actually measuring in inches. So the 4.75 is also a measurement in inches, so let's just add that value to my graph. I don't know exactly where it is, but I do know it's to the left of that standard deviation. that mean. So I've got 4.75 inches. And what I'm looking for, in this case, I'm looking for the probability or percentage of the adult male population that has a head that's too large. So I'm looking for something that's too large. In this case, larger than 4.75 is going to be anything to the right. So I'm going to be shading off to the right. Right now, you don't know the answer to this area, but you should be able to determine an estimation of how large it is. And hopefully you can see that my final answer is going to be larger than 50%. That's a claim because it looks like that. Let's see if that ends up being the case. Luckily for us, we've got a nice little calculator, and it gives us a nice function of how to input this in and determine the area. So we're just going to use that function of just normal CDF because it's a normal curve. We can take the normal CDF, and we're asked to input 4 numbers. The first number is going to be the number we start measuring the area at. In this case, that's 4.75. Then we're going to type in the number we're going to stop measuring the area at. In this case, I'm going to measure that about 10,000. I'm not even going to that. Next step is going to be the standard deviation and the mean. The mean and the standard deviation. Mean is 6.0, standard deviation is 1.0. When I type that into the calculator, I should get a value of 0.89435. So before we move on, let's interpret what's really going on here. What is this? Is this number of inches? Is this a number of people? What is this? This is actually neither of those. It is not inches or people. Oh man, I cannot draw that 9 to save my life. There we go. It is not inches or people. This is a probability. This is a percentage. What this is saying is 89.44% of people lie in that blue region, the region defined by that blue little area. So what that tells me is that if I picked a student randomly, I'd have an 89% chance that they'd have a head larger than 4.75 inches. Wow, that's pretty amazing. The very last problem we've got here, it's the exact same situation as before, so I'm going to go ahead and draw the normal curve. I've got my normal curve with a mean of 6. I'll just draw my curve here. My mean of 6. I've been doing the given information with red, so I'll add that. 6.0, and this is inches. And then I've got my standard deviation of 1 inch. I'm going to add that unit as well. I'm going to clean up this inches down here just because it was messy. All right. Now this problem gets a little bit harder, but it's not too difficult, not too bad. Due to financial constraints, the helmets are being designed to fit all men except those with head sizes that are in the smallest 2.5% or the largest 2.5%. Find the minimum and maximum head sizes that will fit men. So hopefully you're seeing these 2.5% and you're thinking to yourself, oh, I know what that means. That means percent, and when I think of percent, I'm going to think of probability. And when I'm thinking about probability, I'm thinking about area. So what I'm really looking for is the smallest 0.025 area and the largest 0.025 area. All I did was convert those percentages to decimals, but it's very important you take those and make sure you move the decimal the appropriate amount of times. So I'm looking for the area that's defined by the smallest 0.025. Well, if everything under the curve is 1, and I'm looking for the smallest 0.025, I'm going to be looking for an area very small right over here. And this blue area is going to be 0.025. Same idea. If I'm looking for the largest area, all the area under the curve is 1. Well, now I've taken off 0.025 on the left-hand side. And now I want to isolate the largest 0.025 area. To do that, I've got those 2 regions identified, and now what I've got to do is what I'm asked for is find the minimum and maximum head sizes. Well, luckily, my head sizes are down here along the x-axis, and this is what I'm measuring here, the head sizes. So what I'm really looking for is the minimum head size and the maximum head size. So I'm trying to find these values. I'm trying to find the numbers that define those regions. So I'm trying to find the minimum number and the maximum number. That's what I'm trying to determine. Luckily, we've got a nice little calculator function that allows us to do that. And I'll go ahead and define these two in 2 different colors. So let's do this first one in orange. So I'm going to identify this value here in orange. To do that, I'm going to use my inverse norm function. That is just inverse norm. And it's going to ask for 3 numbers. The area to the left of the value I'm interested in. In this case, that's 0.025. Then it's going to ask for the standard deviation, the mean, in this case that's 6.0, then the standard deviation of 1.0. I'm going to go ahead and write out the function for the next one as well, and then I'll type both of these into the calculator. The next one is going to be a very similar function. We're now looking for the value that defines the 0.025 0.025 area on the right-hand side. And again, we're going to be using the inverse norm function. Inverse norm, looking for 3 values. And this gets a little bit trickier. The first value in this inverse norm function gets a little bit trickier. The second two are going to be the exact same. We're looking for the area to the left of the curve for a data that has a mean of 6 and a standard deviation of 1. But remember, this first term is always going to be looking for, the area to the left. So if this is the value we're looking for, where we've got 2.5 over here to the right in that blue area, what I really need to plug into this formula, what I need to plug in that orange circle, is the value to the left, the area to the left. And what's really, really nice, if I know that 0.025 is to the right of this green line, right there. If I know 0.025 is to the right of that green line, I know that the purple area must be 1 minus 0.025, because all of that area must equal to 1 when you add it all up. If you don't see that, that's very important you see where and why that comes up from. So if you're having trouble understanding this formula, make sure you pause the video, think about that one. I bet it'll come to you. But once I've identified what area is to the left of that green line, I need to put 0.975. That's the value that solves that equation. And when I put 0.975 into that equation, I should be able to calculate both of those values. Using a calculator to finish this, I get that the inverse norm, or the area defined by 0.025 on that curve, is defined by a value of 4.04 inches. And then the area defined by 0.975 area is going to be 7.96 inches. So roughly, hats will be sized between 4 to 8 inches, and I'll take either or any of those solutions will be perfectly fine.